Alright, you guys, so today we're going to be doing 4.2, which is going to be graphs of polynomials. So now that you have a general understanding of polynomials and behavior, of degree, now we're going to actually look at polynomials and determine some more key features. So first we have the degree, which we talked about in 4.1. The degree of the function is also the maximum number of zeros, real or imaginary, that the polynomial function can have. Okay, maximum number of zeros. So it cannot have more zeros than the degree of the function. A relative maximum is a turning point on the graph of the polynomial where the function changes from increase to decrease. So for example, here, this would be a relative maximum at point A. Relative minimum, same idea, but we change from decrease to increase. And then we have absolute max or min, which is a turning point on the graph of a polynomial function that is the absolute lowest or highest point on the graph. Now the one in this particular picture here, this is an odd degree polynomial. I know it's odd because it's going in opposite directions. These odd degree polynomials will never have an absolute max or min. The only ones that have absolute maxes or mins are even degree because they're either going to end both upward or downward. So keep that in mind. So a turning point is a point on the graph at which we change from increase, decrease, or decrease, increase, known as a relative min or a relative max. So all relative mins and max or absolute mins and maxes are turning points. Repeated roots. Polynomial equations can have double roots, triple roots, or quadruple roots, and so on. In general, these are referred to as multiple roots. So the roots actually, the amount of times that the root occurs actually affects how it looks on the graph. So I remember talking about this with you guys a long time ago, saying when we get two results, like x equals 2 twice, at the time it didn't matter. We had the single solution of x equals 2. But when the same root occurs twice, in even amount of times, it actually bounces on the graph, as you can see here. See how it doesn't actually cross the x-axis, it actually bounces on the x-axis. And anytime a root only occurs once or any odd amount of times, so once, 3 times, 5 times, so on, it actually will cross the graph. So even multiplicity bounces, odd multiplicity crosses. Very important. Okay. Analyze the graphs of the following polynomial functions. So here we're just going to go through and analyze all of these things. Let me get the pen out. There we go. Okay. So I see that we have 2 turning points. So for number of turning points, I can say 2. Now, the degree of the polynomial is always 1 more than the number of turning points. So this is a 3rd degree polynomial. 3 is obviously an odd number. And behavior. So what does that mean? That means that as my function is going to the left, as x goes to negative infinity, the function's going downward, right? And as my function goes, a different color, as my function goes to the right, it goes up to positive infinity. So over here it's going down as we go toward the smaller x values. And as we go toward the bigger x values, my function goes up. Number of real zeros. So that's how many times we essentially cross the x-axis. So we cross 1, 2, 3 times. So the total number of zeros should add up to the degree of the polynomial. So in this case, we have 3 real zeros, so we don't have any space for any imaginary zeros. The domain for any odd degree, or any polynomial, is always negative infinity to positive infinity. But the range for any odd degree polynomial is also negative infinity to positive infinity. Even will have some kind of constraint on the range. Domain will be all real numbers. Range will be constrained by the fact that it's going to have a minimum or a maximum. So now we're going to identify those relative mins, relative maxes. As you can see, we have a relative max, and here we have a relative min. So it looks like my relative max occurs at 0.5, comma, 1.5. And then we have a relative minimum at 2, comma, -1. Y-intercept, we have a y-intercept here, and that is occurring at 0, 1. And then increase, decrease intervals. So I'm going to erase everything on here. So I'm going to do my decrease in red, I'm going to do my increase in maybe yellow will do. So we're decreasing from here until we get to here, right? Oh, that's too opaque. Here we go. So we're decreasing. And then here and infinitely we are increasing, right? So remember, increase, decrease intervals are only based on x. The y is the increase and decrease part. We're only looking at the interval on x at which we're increasing and decreasing. So it looks like my function is increasing from -infinity until we get to this boundary right here at 0.5. And then my function increases again at, looks like 1, 1.5, or sorry, 2.5. Yeah, that's 2.5. To positive infinity. Now, hang on, relative min. Oh, it's actually just 2. I'm overthinking it. Don't mind me trying to get it precise. Yeah, it's actually just at 2. It kind of looks like it's at the 0.5, but okay. So that's where we're increasing, and then we're decreasing from 0.5 to 2. So you're going to see that one always picks up where the other one leaves off. See where the red is decreasing, where the yellow is increasing. Okay, so this one here, we have a turning point here, 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 and here. That's 4 turning points. And the degree of the polynomial is always 1 more than the number of turning points, so it's 5. Of course, 5 is an odd number. As my function goes out to the left, that's what this means. To the left. And this one is to the right. So as we go to the left, my function is going down. And as we go to the right, my function is going up. Number of real zeros, this is how many times we cross the x-axis, which is 3 times, which means that my imaginary zeros is 2, because these two numbers have to add up to the degree of the polynomial. The domain for every single polynomial function is all real numbers, and the range for any odd degree polynomial function is also -infinity to positive infinity. Oh, I forgot the identification part. This is cubic. I think that's what, identify. Oh, identify max or min. Oh, it just wanted us to, never mind, we already did it. Don't mind that. Relative maximums. So we have a maximum here and here. So all those turning points are either going to be relative maxes or relative mins, one or the other. So we have one occurring at -2, comma 2.5. And then we have another one occurring at 1, comma -1. And then we have the minimums at 0, comma -1. And then we have one at 1 to 2.5, comma -2. The y-intercept is 0, comma -1. And then our increase-decrease intervals, of course. So we're increasing here, And then we increase a little bit here and here. And then everything in between is decreasing. Now there could be constant in functions as well, so look out for that, but not in this case. So it looks like we're increasing from negative infinity to negative 2. And then we're increasing again from 0 to 1. And then we're increasing again from 2.5 to positive infinity. So you're going to notice that the relative mins and maxes will correspond with the increase-decrease intervals as well, because those are the turning points. That's where we change from increase to decrease and vice versa. And then decrease, we're decreasing from negative 2 to 0. And then we're decreasing from one to 2.5. You see how they correspond with each other? These correspond, and then these correspond. The increase pick up, or the decrease leave off, and vice versa. So, leading coefficient. In this case, my leading coefficient, we're starting down and ending up. Anytime you end upward, your leading coefficient is positive. That's how you can determine that. All right, so now we're going to do the next page. Okay, repeated roots. Okay. Just making sure I read it right because I'm like looking at clips of the papers. All right. So this one here. No, we don't need a ruler. Put that away. Not for this class. Okay, maybe one day though. So repeated roots. Polynomial equations can have double roots, triple roots, quadruple roots. Cannot say that word, and so on. In general, these are referred to as multiple roots. Okay. So let's identify the type of polynomial. There's 3 turning points, which means that it's a 4th degree polynomial. Degree is always one more than the number of turning points. And 4th degree, we call that quartic. And behavior, as you can see, as we look to the left, we're going up, and as we look to the right, we're also going up. So the end behavior on both sides is positive infinity. Anytime you end upward, like I said, it means we have a positive leading coefficient. State the real zeros and the multiplicity. Okay. So, as you can see, we have a 0 here, here, and here. So, we have a 0 at negative 4. And that's an odd multiplicity because it goes through the axis. See how it goes right through it? Crosses. Axis. And then we have another one. Oh, that's why it goes on to the next page. I was getting confused because there's 3. And then we have another one at negative 2, 0. And that one is also odd because it crosses. And then we have one last one at 3, 0. And that one is even because, as you can see, it doesn't cross, it bounces. It bounces on the axis. Relative mins, relative maxes. So we have our mins here. We have one at negative 3, comma, I think that's about negative 1.5. We have one at 3, 0. Oh, I did that wrong. This is relative maximum. Oops. So relative maximum is this one right here, which is at about 0, 3. And then we have a relative minimum at 3, 0. Minimum. Maximum. And then we have an absolute minimum here, because that's the lowest that function's ever going to go, which makes it absolute, which is at -3, -1.5. So just to clear things up, absolute minimums or maximums are also still relative minimums, maximums, but they're also additionally absolute. Okay, write one possible equation in factored form for the function above. Okay, so we know we have a 0 at -4, which means that the factored form of that, it always switches signs, is going to be x plus 4. If we were to set that equal to 0, it would give us -4. And then we also have one at -2, which is going to be x plus 2. And then we additionally have one at 3. So that's x minus 3. But we see that that bounces on the axis, right? So when you bounce on the axis, that means that 0 has to occur more than once. It has to be an even amount of time, so we're going to square that. Now, we know that this particular polynomial is quartic, and its ending on end behavior is even positive. So the leading coefficient has to be positive, which this is. It's an implied 1 there. We don't have to write it, so we don't have to negate that or anything like that. Alright, and the last page, sketch the polynomial given the characteristics. We don't want to delete it. Okay, so sketch the graph of the polynomial functions with the following characteristics. Alright, so we have a 0 at -5, -3, 0, 2, and 4. It's an odd degree function, which means they're going to end in opposite directions. But the end behavior is going to tell me which way it's going to go on each side. So that means that on this side it's going to be going upward, on the left side it's going to be going upward, and on the right side it's going to be going downward. And I got that from here. Let's use a different color. There we go. Okay. So I can draw something like this. And we want to make sure that checks all the boxes off. Okay. So yeah, looks good. I don't know why this formatted weird when I saved it as a PDF, so I'm just going to write the other function over here. I know it looks confusing because it's on the wrong side, but here's the one that we're looking at. So don't worry about that here. Okay, so that's the sketch for that one. The sketch for this one. This tells me I have a 0 at -2, +1, and +3. But the 0 here occurs twice, so it's going to have to bounce at 1. So I'm going to have to make sure it bounces. This right here is going to be a fourth degree polynomial. Now, how did I know it was a fourth degree? You could go ahead and technically multiply this whole thing out if you wanted to, but I wouldn't recommend it. But you can just count the number of x's. 1, 2, and then this x occurs twice. 3, 4. It's a fourth degree polynomial. And this leading coefficient is positive, right? So this is even positive, which means that the end behavior is going to look like this. So it's going to start upward and end upward, and remember we have to bounce at 1. So that's what it's going to look like, something like that. Now, we don't have to worry how much we go down and up on our relative maxes and mins without specification if we're just doing a sketch. Determine the end behavior, I kind of already did that. It's even, positive. Find the x-intercepts. We got one at x equals -2, x equals 1 and x equals 3. That's just by setting each one of these separate factors equal to 0. And then graph and sketch. So we could also find the y-intercept as well to get more accurate with where we land right here. We can do that by just simply plugging in 0 for all the x's. So I'm just taking my polynomial and I'm plugging in 0 for all the x's. So this gives me 2, and then negative 1 squared is 1, and this is negative 3. So that gives me negative 6. So I really would have wanted to go down a little more on this, so I'm going to redo this part. So I know I have a point here. So it's going to look something like this. So that's going to give you a better idea of where your sketch is going to be. Gives you a little more information to make your sketch a little more accurate if you have the y-intercept. Alright, and the last one, given the polynomial graph, given a polynomial graph, identify characteristics. Okay. What is the local or relative maximum on the interval of negative 2 to negative 1? That's here. Which looks like that would be this, right? So that's about 1, 2, 3, 3.5, so 3.7. Okay. What is the local or relative maximum on the interval negative 1 to 1? So that's this interval. So they want to know the relative max. So we have a min and a max, so we're going to look at the max. And that looks to be at about like 1.5, so 1.4. So yeah, that's it.